Hello, today we're covering statistical significance, arguably the single most important and most misunderstood concept in all of research and analytics. If you've ever heard someone say a result is statistically significant and nodded along without being sure what that actually means, this video is for you. By the end, you'll know exactly what statistical significance is, what the p-value tells you, and critically, what it doesn't tell you. Let's start with the problem. Here's the fundamental challenge with any research results. It's based on a sample, not the whole population. You didn't survey every customer, you surveyed some of them. You didn't run the experiment on every user, you ran it on a subset. And samples vary by chance. Even if there's no real difference between two things, you might see a difference in your sample just because of random variation in who ended up in each group. So how do you know whether the difference you found is real, or just a coincidence that showed up in your particular sample? Statistical significance is the answer to that question. It asks, for any given result, how likely is it that this happened by chance? If the answer is very unlikely, the result is probably real, and you can act on it. If the answer is quite possible, you can't yet rule out that you're looking at random noise rather than a real effect. One important thing to understand up front: statistical significance doesn't tell you that a result is important or large. It just tells you it's probably not a fluke. Those are different things, and we'll come back to that. Statistical significance is a way of determining whether a result observed in a sample is likely to reflect a real effect in the broader population, or whether it could plausibly have occurred by chance. The answer is never certain because you're working from a sample rather than the whole population. It's always a probability, but statistical significance gives you a principled, consistent way to decide when a probability is low enough that you're comfortable treating the result as real. Here's the intuition that makes this click. Imagine you flip a coin 10 times and get 7 heads. Is this a biased coin or just luck? It's really hard to say. Getting 7 out of 10 to heads is unusual, but it's not that unusual. It could easily happen by chance with a perfectly fair coin. But now imagine you flip the same coin 1,000 times and you get 700 heads. That's a very different situation. Getting 700 out of 1,000 heads when the coin is fair is astronomically unlikely. Almost certainly, the coin is biased. Statistical significance applies exactly the same logic to your research results. Given your sample, how likely is it that what you're seeing happened purely by chance? Let's make this concrete. Freshbox is a meal kit subscription service, and they're running an A/B test on 2 email subject lines to see which drives more opens. Version A is, your meal kit is waiting. It gets a 24% open rate. Version B is, cook like a chef tonight. It gets 27%. That's a 3 percentage point difference. The question is that a real 3-point gap? Or is version B genuinely better? Or did it just happen to have a slightly better result in this particular sample by random chance? That's exactly what statistical significance will tell us. Before we can test the result, we need to set up the test properly. We start from the null hypothesis, the assumption that there is no real difference between the 2 subject lines, and that any result we see is just random variation. In other words, we begin by assuming version A and version B perform equally, and what we observe in the data is just noise. The goal of the significance test is to gather enough evidence to confidently reject that assumption. If we can reject it, if the evidence is strong enough, we declare the result significant and conclude that the difference is real. Here's the key number that comes out of the significance test, the p-value. The p-value is the probability of seeing a result at least as extreme as yours, assuming the null hypothesis is true, meaning there's actually no real effect. For Freshbox, the p-value is the probability that we'd see a 3-point gap in open rates just by random chance, and if there were truly no difference between the two subject lines. A p-value of 0.05 means if there were truly no difference, there's only a 5% chance we'd see a gap this large or larger by random variation alone. The lower the p-value, the less likely the result is random, and the more confident you can be that the effect is real. The standard convention in most research is to require a p-value below 0.05 before declaring a result statistically significant. That's equivalent to saying you have 95% confidence the result is real and not random. Why 0.05? It's mostly historical convention. The research field settled on this threshold decades ago as a reasonably balanced between two types of error: false positives, where you call something real when it isn't, and false negatives, when you miss a real effect. It's not a magic number or a law of nature. It's a practical standard that most disciplines use for consistency. Some higher stakes fields, medical research for example, use 0.01, requiring 99% confidence. Let's see how Freshbox results play out. The 3-point open rate difference between version A and version B. In scenario 1, the p-value comes back at 0.03. That's below the 0.05 threshold, statistically significant. There's only a 3% chance this gap appeared by random variation. Freshbox can confidently roll out version B. In scenario 2, the p-value comes back at 0.12. That's above threshold, not statistically significant. The same 3-point difference, but with a smaller sample or more noise in the data. The test can't rule out that this happened by chance. You can't call a winner. And notice, same size difference, two completely different conclusions. That's why sample size matters so much. There's a related concept that often gives you more useful information than a p-value alone: the confidence interval. Instead of just giving you a yes or no significance, a confidence interval gives you a range within which the true effect almost certainly falls. For Freshbox, at 95% confidence, the true open rate difference is something between 1.1 and 4.9 percentage points. Two things that range tells you. First, it doesn't include 0, which confirms the result is significant. Because if 0 were in the range, no difference would still be plausible. Second, it gives you a sense of the practical size of the effect. The true difference is probably at least 1 point and probably no more than 5. That's more useful than a p-value alone. Here's why sample size is so central to statistical significance. Larger samples reduce the random variation in your results, which makes it easier to detect a real effect with confidence. Freshbox, with 100 subscribers per group, the 3-point open rate difference produces a p-value of 0.21, not significant. Freshbox with 1,000 subscribers per group, the same 3-point difference produces a p-value of 0.03, significant. Same effect, different conclusion, because the larger sample reduced the noise enough to see the signal clearly. This is why planning your sample size before running a study matters so much. An underpowered study, one with too few respondents, can miss real effects and lead to wrong decisions about what's working. Here's the misconception that causes the most damage in research. People equate statistically significant with important. They are not the same thing. Look at the 4 quadrants. A result can be significant and important, real and large enough to matter for your business. A result can be significant but not important, real but so small that it doesn't meaningfully affect anything. With a sample of 100,000 people, a 0.1 percentage point difference in open rates can reach statistical significance. It's still a 0.1 percentage point difference, probably not worth changing your email strategy over. And a result can be important but not significant. The effect looks meaningful but your sample was too small to confirm it statistically. You always need to ask both questions. Is the result significant? And is the effect size large enough to actually matter? One more important clarification. A non-significant result doesn't prove there's no effect. It means you couldn't detect one with the data you had. There are two very different reasons a result might not reach significance. The effect might be real, but too small for your sample size to pick up, you need more data, or the effect might genuinely not exist. A p-value above 0.05 tells you the evidence isn't strong enough to conclude the effect is real. It doesn't tell you we've proved the effect doesn't exist. That distinction matters enormously for how you interpret and communicate results, especially when a test comes back non-significant and stakeholders want to draw strong conclusions from it. Let's be balanced. The strengths of statistical significance. It provides a principled, consistent standard for deciding when a result is trustworthy. Without it, every researcher would have their own thresholds and results would be incomparable. It's widely understood across research and business contexts, and it gives a clear yes-no that simplifies decision-making. The limitations are significant and worth knowing. The 0.05 threshold is a convention, not a law. There's nothing magical about 5%. Large samples can make trivial differences significant, which leads to resources being spent on things that don't actually matter. P-values are among the most widely misunderstood and misreported statistics in all of research. And significance tells you the result is real, not that it's important. Always pair significance with effect size for the complete picture. 6 things to take with you. Statistical significance asks whether a result is likely real or could be random chance. It's always a probability, never a certainty. The p-value is the probability the result occurred by chance alone. Below 0.05 is a standard threshold for declaring significance. Confidence intervals show the likely range of the true effect and tell you whether 0 is a plausible outcome. Larger samples make it easier to reach significance by reducing random noise. Significant does not mean important. Always check the effect size, because a tiny real difference isn't necessarily worth acting on. And not significant means you couldn't detect an effect, not the effect doesn't exist. Get these distinctions right, and you'll interpret research results far more accurately than most people do. Thank you for watching.